Okay, so this is the next question that we got on the menu today. It is asking us, a generator uses a coil which has 160 turns and operates in a zero point 0.5 Tesla magnetic field. The frequency of this generator is 60 hertz, and its electromagnetic field, electromotive force, has an RMS value of 120 volts. Okay, so its voltage, basically it's saying its voltage is RMS 120. Assuming that each turn of the coil is a square, okay, that's pretty important. Determine the length of the wire from which the coil is made. Okay, so let's extract the information of interest out of this question. Okay, so of interest. So the first thing that we are given is 160 turns. So that's going to be our n value. 160 turns. And our magnetic field is represented with B. That is 0.5 Teslas. Okay. The frequency is 60 hertz. 60.0 hertz. And its voltage, or let's just call that EMF. This is equal to 120 volts RMS volts. And something of interest about these turns is that assume each turn is a square. And that is definitely a square. That's not a rectangle. Don't worry about that. Okay, so we have to determine the length of the wire. Now to do that, we need to get our equation that is going to be corresponding to this. So the equation that we want to use is this one right here. This is a pretty common coil equation that is commonly used. So our here is our epsilon, or our EMF, is equal to our number of turns times the area times our magnetic field times our angular frequency. Okay, so angular frequency, B comes from here, N comes from here, and this is cross-sectional area of coil. Okay, and an EMF, well, that's pretty straightforward. But we don't really know the area, but we know that the area is going to be square, right? So cross-sectional area of the coil has to be a square. And let's say area is equal to its side length squared. And that makes perfect sense because we know that it's a square. That means all side lengths have to be the same. And well, the area of a square, length times height, even though they're the same, is just L squared. Okay, so we could rewrite this as let's just say that this is equal to V. Just so it's a little bit easier to write. So we have V equals N. Instead of A, we'll have L squared. B, instead of angular frequency, this will be 2 pi F is equal to omega. So we can just do 2 pi times the frequency we gave us, because the frequency that we were given is in hertz. So we need to convert that to radians per second. We just multiply 2 pi to that. Fairly straightforward. Okay, now we are trying to find the length of the wire, and which means that we're trying to isolate L. L is just the side length, but the total length of the wire, well, we'll see how we proceed with that. Think about it for a second. Okay, so isolate L, because everything else is given to us. So we'll have V over NB 2 pi frequency is equal to L, and we have to square root the left side because the right side would have had L squared before we did that. Okay, so we can possibly sub in our numbers. So we get a similar looking thing here. Oh, another thing that we need to mention is this is for the peak. Yikes. Peak voltage. We know that V peak is equal to root 2, which is about 1.4 times V RMS. Okay, so yeah, that's my bad. I'll make a correction real fast. So this will be so root 2 RMS, and then a root 2 term. Okay, and just to go back up here, just to make things super clear, peak voltage. Okay, so now everything should be in order. Okay, so yeah, so now we have our isolation for this. Now we can sub in our numbers to get our L. So our RMS value was given as 120 volts. So we have root 2, 120 volts, N was 160 turns, B is 0.5 Teslas, 2 in pi, well, those are just numbers, and our frequency was given as 60 Hertz. Okay, so let's run this through our calculator. So square root of 2 times 120 divided by 160 times 0.5 times 2 times pi times 60, close the bracket, and then put that whole thing to the square root. And my calculation for that L is 0.075 meters. So what we got here, .075 meters. Awesome. Okay, so this is the side length of one, or the side length of one turn of the coil. The total length of the coil, as we can see here, is like actually, I think I have a pretty good model here, because I actually do have some real life wires and kind of show what's going on here. So make my camera a little big for a second. Okay, so here, you know, it's a fairly straightforward blue wire. Hopefully you can kind of see it well. But as we make it a coil, we're kind of making it into something like this. Okay, so you can see like this is camera focus, please. Well, you can see like this, we only found, like if this was a square, we only found this here. But the total length of the wire, you recognize that, well, the entire area, if we only know the length, we know that one loop is going to have 4 times that, assuming it's a square. These things don't tend to want to be squares. But yeah, one side is going to, one coil, one turn is going to be 4 times the side length. And we have, well, we have a lot of turns, 160 of them. So that, we'll have to multiply that to get the total length of the coil. Okay. So L total is equal to 4 times L times N. So these two terms are going to be one turn. And this is just number of turns. So L total is going to be 4 times L, which is 0.075 meters, multiplied by 160 turns. And this is going to be something that I asked my calculator, times 4 times 160. And I get 48 meters. Is that what we got here? Yeah, so okay, so this is the total wire length. And this is a fairly reasonable answer, like 48 meters, that's, you know, it might take you like 5 or 6 seconds to sprint that at full speed, but it is reasonable to see a coil that long because they are really rolled up 160 times. It's like kind of how people say every vein in your body laid end to end could go around the earth a couple times. Like when you really roll these things up, they really do get a lot smaller in size, and they can get pretty long, even if the coil is like only 7 centimeters per each side. Overall, it can be 48 meters, which is fairly large, but reasonable. Okay, so this above solution is actually very good, and that's awesome. Cool. Awesome. Beautiful.